I hope all of you have got the hard copy of this group 17, which is the chemistry of the group 17, the halogens. Last week we completed the 10A, which is the study of the group 2. In this chapter, we'll be studying about the chemistry of the halogens, which is the group 17. In fact, the group 17, we used to call it as group 7 before. Group 7 or the group 17 is called the halogens because it is in Greek halo, gen, the word halo and gen. Halo means in Greek salt, gen means form. So it's a Greek term, halogen. It's a Greek term. Halogen is called the halogen in short, right? So all the halogens, and you say halogens, you have these halogens in the group 17, fluorine, chlorine, bromine, iodine, and astatine. There are 5 halogens, out of which the fluorine and the astatine, the chemistry of it, we don't study. The reason being, the fluorine is highly reactive. That in fact, the most reactive halogen is fluorine. The reactions of fluorine are very violent, and we don't have fluorine in our school laboratories because it's very violent reactions. And also, when the chlorine reacts and forms compounds, such compounds are highly stable. Fluorocompounds are difficult to break. For example, the carbon-fluorine bond is very inert. You can't break the bond. Likewise, the astatine is radioactive. So we don't study those two extremes, but we study the other 3, which is chlorine, bromine, iodine, the chemistry of these 3. So based on the chemistry of these 3, chlorine, bromine, and iodine, you should be able to predict the chemistry of fluorine and astatine, right? Fluorine and astatine. Now, thing is, the chlorine is a pale green gas, right? Poisonous gas, and they all are poisonous. In fact, they all have a similar strong smell. Bromine is also diatomic molecule. Poisonous, is brown color liquid with red-brown vapor. Iodine is a solid, which is a gray solid with purple vapor. So you can notice here, these are all diatomic molecules, and they all are non-metals, and they all have a similar strong smell, right? And the physical state changes from chlorine being a gas, bromine is a liquid, and iodine is a solid. So physical state changes from gas to liquid to solid. So they all poisonous, similar, have similar strong smell. They all are non-metals, and the boiling points increase as you go down the group because these are diatomic molecules, simple covalent molecules. The boiling points of simple covalent molecules are determined by the strength of the intermolecular attractions. So what is the type of intermolecular attractions do you find between halogens? Yeah? What is intermolecular type? What's the London forces? That's right, dispersion forces, London forces. Or induced dipole attractions, because they're non-polar molecules. And we know the strength of the dispersion London force depends on the number of electrons. So number of electrons increases from chlorine to bromine to iodine. That's the reason for the increase in the strength of the dispersion force, because that accounts for the increase in the boiling and melting points. And also their physical state. That's the reason for physical state to change from gas to liquid to solids. Right? They all form diatomic molecules, and you can notice the intensity of the color of these gases increases, of these diatomic molecules increase. Chlorine is a pale green. Fluorine is a pale yellow gas. Chlorine pale green. Bromine is brown liquid. Iodine is a gray solid. If you heat iodine directly, it sublimes. It will go into the gaseous state directly. That is sublimation. So iodine, there's no liquid iodine, rather it sublimes. Iodine sublimes, and there's no liquid iodine, right, to a purple vapor. So that's for the chemical properties of the group 7 halogens. So they all have 7 electrons in the outermost shell. So therefore, as a result, they all show similar chemical properties. And as you know, down any group, the atomic radius increases. Likewise, the halogens. So halogens gain electrons. So when the atom is small in size, it's easy to gain electrons. So therefore, the fluorine is the most reactive one, and the iodine or the astatine is the least reactive. In fact, astatine is dark, almost like blackish color. So the reactivity will decrease down the group because halogens gain electrons, so the atom is small in size. It's easy to gain electrons, so the fluorine is the most reactive and the iodine is the least reactive, right? So, and also because halogens, they gain electrons, they undergo reduction. Gaining electron is reduction. So they are good oxidizing agents, right? So the strongest oxidizing agent is found at the top, which is the fluorine, and the weakest oxidizing agent is found at the bottom because they themselves undergo reduction by gaining electrons. So therefore, they are good oxidizing agents. And all the halogens, they react with metals to form salts. That's why we call halogens as salt formers. In Greek, we say halogen. Halo is salt, and gen is form. As for the electronegativity, that's the ability of atom to attract the bonding pair of electrons itself. That will decrease down the group. The most electronegative halogen will be the fluorine, and the least will be the iodine or the astatine. As for the description of these elements, we can write the description here. Fluorine, pale, yellow gas, smelly and poisonous. Please write the description. Fluorine is pale, yellow gas, smelly and poisonous. Chlorine, pale green gas, pale green gas, smelly and poisonous. Chlorine is pale green gas, smelly and poisonous. Bromine is brown liquid. Smelly and poisonous. Iodine is gray solid. Gray solid. Smelly and poisonous. That's a gray solid with purple vapor. Smelly and poisonous. Gray solid with purple vapor. Smelly and poisonous. So the variation of the states and the melting point down the halogens, right? All halogens form diatomic molecules in the vapor state. These molecules are non-pole and they form temporary fluctuating dipoles. Hence, the intermolecular forces are dispersion London forces. The strength of the dispersion force increases down the group as the number of electrons increase. And also, the larger molecules are more polarizable than the smaller molecules. As a result, the melting and boiling temperature increases down the group. This indicates that the fluorine and chlorine and the lowest number of electrons will form the weakest attraction. Therefore, they exist as gases, whereas bromine, stronger dispersion force compared to chlorine. Thus, a liquid, and it has the larger number of electrons, form the strongest dispersion force, and therefore the solid at room temperature and pressure. I'll discuss about it. And as for the reactivity of the halogens as oxidizing agents, halogens, they have 7 electrons in the outermost shell, so they gain electrons and hence undergo reduction. Therefore, they're good oxidizing agents. The strongest oxidizing agent is the fluorine, and the weakest being iodine, right? So you can copy this. The halogens gain electron and form the halide ion. Let's copy this. The halogens, all the halogens, they react with hydrogens to form the corresponding hydrogen halide. And we know the chlorine will react with hydrogen to form hydrogen chloride. Likewise, bromine forms hydrogen bromide, and the iodine forms hydrogen iodide. So ease of reaction decreased down the group. The hydrogen with chlorine is the most violent and vigorous, and the iodine with hydrogen is the weakest. Please copy these three reactions. So all these hydrogen halides, they are acidic, right? They in aqueous media they can easily release H plus ions. So that's why they're acidic. In fact, the acidity depends on how easy the H plus can be released. So you have hydrogen chloride, hydrogen bromide, and the hydrogen iodide. In fact, the hydrogen iodide is the strongest hydrogen halide acid because hydrogen iodine bond is the longest bond, which is the weakest. Long and weak. Short bonds are strong bonds, right? So the HCl bond is short, HI bond is long, therefore it's weaker. Hence, easily it can be broken and release H plus ions. So that's the reason why the hydrogen iodide, being the strongest hydrogen halide acid, then comes the hydrogen bromide and then the hydrogen chloride. So the acidity and the thermal stability of the molecule depends on the strength of the HX bond. So in thermal stability wise, hydrogen fluoride or hydrogen chloride are the most thermally stable, and hydroiodic is least thermally stable. So thermal stability increases in this order. Hydrogen iodide is the weakest, then comes the hydrogen bromide, hydrogen chloride, and the hydrogen fluoride. That's the most thermally stable. Right, you can copy this. And as for the acid strength of the acidity, all the hydrogen halides are acidic because in aqueous media it releases H plus ions to water. Therefore, that makes it acidic. Except for the hydrogen fluoride. Hydrogen fluoride is a weak acid because hydrogen and fluorine bond is quite hard to break. It's not so easy to break like the hydrogen iodine bond or hydrogen chlorine bond. The hydrofluoric acid is a weak acid because it's difficult to break the HF bond. So the HF is a weaker acid and the HI is the strongest acid. The acidity will increase in the order of HF to HI. But all hydrogen halides are acids, all are strong acids except for the HF, which is a weak acid. For HF, we know there is hydrogen bonding. So all hydrogen halides at room temperature, they are gases except for hydrogen fluoride, which is a liquid because it has strong hydrogen intermolecular forces. Let's look at the test for these halogens. Remember, the test for the halogens is different to the test for the halides. Halide is test for the iron, chloride, bromide, iodide. Test for halogen is test for the chlorine, bromine, iodine. Test for the chlorine, as you all know, it bleaches the litmus paper, right? If you have, say, blue litmus, it turns red first, and then it bleaches afterwards, right? If you have say red litmus, the presence of chlorine, directly it bleaches, right? As it is for the chlorine gas, right? Bleaches the litmus paper. We can have a look at this. Just for the chlorine. This is a damp. We have two litmus papers here, the red litmus and the blue litmus. We have to first moist it and then keep it exposed to the chlorine gas, right? And then when you carry out the reaction which releases chlorine gas, the blue litmus will turn red first because chlorine gas reacts with the moisture in the litmus paper and form hydrochloric acid. That's the reason why blue litmus first turns red and then it turns white, bleaches. The red litmus, it directly bleaches it because red litmus, the presence of chlorine, it turns white directly. It turns white directly. So that's the test for the chlorine gas. And notice the litmus paper now. The end result, you can see it has turned white. Well, it must have turned red, and then it has turned white. And also you can use the displacement reaction. Displacement reaction is a reaction where more reactive halogen displacing the less reactive one. So you have KBr, potassium bromide. If you bubble chlorine gas through potassium bromide, you get bromine. You get bromine, right? Bromine, which is brown color. So a brown color solution is formed. Brown color solution is formed when you bubble chlorine gas through potassium bromide. So that is also a test for the chlorine gas. As for the bromine, as we know, bromine, the alkenes decolorize as bromine, right? That's the test for the bromine gas. In a test with the alkenes, it's very important that you need to know the alkene when you react with the bromine. This bromine water, right? So it forms two layers. It forms two layers, and because bromine water is dissolved in water, and this is alkene, is organic layer, right? It's organic layer. So it will form two different layers, and then it will decolorize. Not immediately, because I would say there are two different densities. Let me show that video.
Three test tubes. On the left, I have an alkane molecule. In the middle, I have an alkene molecule. On the right, I have a fairly concentrated bromine water solution. First, I'm going to use a pipette to put some bromine water into the alkane molecule. You can see that the bromine water turns a dark yellow color. Now let's do the same thing with the alkene molecule. You can notice that when we put in the bromine water, it forms two layers and doesn't dissolve like it did in the alkene.